we've developed a lot of different building blocks so far, right? I mean, we've talked about amplifying stages, we've talked about compound stages, we've talked about single-ended to differential conversion, we've talked about differential signaling to begin with, then we've talked about generating currents and biasing techniques, we've talked about driver stages, but now it's actually an interesting time because we can actually start building bigger systems with these. So we will continue doing that, and we try to construct more complex blocks with these and see what that process looks like. So let's start with let's say with MOSFETs, and let's say we want to build OpAmps with MOSFETs, MOSFET OpAmps. So what is an OpAmp? Let's say we want to make an operational amplifier. An OpAmp, in essence, is a block with a differential input, and a standard OpAmp is a single-ended output, right? So we are trying to make a block. This is obviously the symbol for it. I'm sure everyone is familiar with it. It has two inputs, a plus and minus input, and an output. And then the output essentially is some A times V in plus minus V in minus. Or you could call it VIP minus VIN. Right? And you want this gain to be large. Now, there are other properties of OpAmp. You want an OpAmp, for example, to have reasonably high input impedance if it's used as a voltage amplifier, because you want it to be a good voltage sensor. You want it to have a reasonably low output impedance in general if you want to drive a load. Now, it depends on what kind of a load you want to drive. Sometimes you drive a capacitive load. In that case, you don't care really about the output DC resistance. If you're driving a resistive load, you do care about that output DC resistance, like when we were talking about the output stages, for example. So the key question is that what is the simplest block that does this? Isn't this just a single-ended to differential to single-ended converter? So what is the simplest OpAmp we can construct with MOSFETs? Let's construct it. Let's construct the simplest OpAmp. Let's start with that. Well, the simplest OpAmp would be a differential pair with an input, differential, and then a differential to single-ended conversion using a current mirror, for example. So this can be V out, and this is V in P, VIP, let's say, and VIN, right? And there's a current source here. We'll have to deal with that soon, but we'll deal with that in a second. Let's worry about it in a second. So if you have something like this, we've talked about this, right? We've analyzed this. What is the gain of this thing? Well, if this is the GM of these transistors for a differential input, this is going to be VID over 2. This is going to be negative VID over 2. This is going to be GM VID over 2. This is going to be, well, you can change the polarity. You can say this is going to be GM VID over 2 because it was negative here. So I changed the polarity of that. And this current is going to be reflected here. So this is going to be GM VID over 2. Both of these are injecting current into this node. Right? The two current sources, each injecting GM VID over 2. What is the total resistance on that node? From that node to ground equivalent. From a differential perspective, this is a differential ground. So you see RON here, ROP here. So your overall gain, of course, is a combination of these two, which can be easily seen to be GM of N, these guys, RON parallel ROP. And we've done similar calculations for this thing, right? We can calculate the gain, et cetera, et cetera. We can do it now, and we'll do it in a second. But that's basically what the gain of this thing is as an OpAmp. Okay. Let's say we pick some numbers, right? I mean, and we can do some calculations. Let's say we pick numbers so that GM is 4 millisiemens, and we'll come back to the actual W over L's, and ROs are, let's say, 25 kilo ohms. Let's say for the sake of argument, then you get a gain that's basically in the range of 100, something like that. That's actually pretty high. So let's make this actually 10, or well, let's keep it 25. Doesn't matter. You can get something like that. Doesn't matter. So you get something like in the order of 100, a gain of 100. from this. And again, we can do it more quantitatively. We'll do a lot more based on W over Ls and all those things going forward. But just let's start with this. Let's say these are some of the numbers you're starting. So your maximum gain you can get is 25 kilo ohms, let's say parallel with 25 kilo ohms times 4 millisiemens. That's going to be 50, right? So the gain of this stage is going to, this is going to be 50. Now, you can say, is this a good OpAmp? Well, it depends. Good OpAmp for what? If you're trying to use a simple capacitive load with sufficient gain that you have, you can take advantage of a gain of 50, yeah, this is a great OpAmp. If you are trying to make something with a gain of 1 million, obviously this is not you're not there yet. We'll get there, but in steps. But let's say this was, so what are the good and bad things about this OpAmp? Let's talk about this as an OpAmp. Well, the gain is low, it's 50, that's known. What is its input impedance? DC input impedance. For a classical MOSFET, what is it? Infinity, right? It's an open circuit, essentially, right? What is its output impedance? It's RON parallel ROP, right? It's 12.5 kilo ohms based on the numbers that we just conjured up, right? So it's 12.5 kilo ohms. Is it a good thing? Well, depends on the load. If you're driving a resistive load, let's say I'm driving a 50 ohm load for the sake of argument. Let's say I was driving a 50 ohm load. Now, is this a good OpAmp? Why not? What changes? What did change? What did just change? In parameters of the OpAmp. Did its input impedance change? No. Right, so the gain changed. So my new gain is this guy parallel 50 ohms, which is going to be 12.5 kilo ohms parallel 50 ohms, which is 50 ohms, times 4 millisiemens. What's my gain? 0.2. So it's a nice attenuator. It's not a good attenuator. A resistor is a better attenuator than that because it's nonlinear too. But anyway, so it's obviously not going to work like that. But if I'm driving a high impedance load and all those things, we'll get to these things that do better than that in a sec, or in a little while. But that's what it is. But now let's say this is fine with what we wanted to do. Is this still an OpAmp? Is it functional? Let's say my load was a capacitive load, so I don't have to really worry about this kind of a resistive load. Is this an OpAmp? Are we done? Is it complete? Obviously, there's an ideal element here. It needs to be taken care of. So how do we do that? How do we take care of this? So I want you to help me here. What do I do with this? You can't go to the stockroom and get a current source. Even if you could, you can't put it on the chip. So what do we do? What do I put here? What do I put here? A transistor, right? So you can put a current mirror here. And then bias it with this I reference. I say, oh, come on. You took that I out and then you put another one here. Well, it's not as bad. Because now this thing can be a lot of different things. For example, if you want to make it very independent of supply and temperature, and we'll do that, you can use all of those techniques that we use. We can use some of those reference currents that we generated. But if we were really, really kind of like wanted for something quick, looking for something quick and dirty, you can actually put an RF here. Yeah, this will become supply dependent and everything, but yeah, I mean, this can generate a reference branch, replicate it here, use it as a reference current, and this is your most basic OpAmp. Is it a good OpAmp? No. But that's the most basic OpAmp. Now, we need to make sure that we understand what this does and how this works because we are going to build up a lot. So every step needs to be clear. Okay? So is it clear what everything in this very simplistic OpAmp does? Right? What do these two guys do? It's a differential pair, right? It converts the differential input to a differential current, differential input voltage to a differential current. If you apply common mode, if this current source is a good current source, that output voltage common mode is not going to change because the sum of them are forced to be constant, right? What do these two do? It takes one of those currents, reflects it here, copies it here, so you can actually combine them into one node and you get a single-ended conversion. What does this guy do? It uses the output resistance of a transistor to emulate a current source to present a high output impedance. RO of this transistor is the output impedance of this thing. That's it. What is this one doing? This is a current mirror. Establishes the voltage for the gate of this guy based on the current here. What is this resistor doing? Well, the difference between this VDD and this VGS will drop across that. It sets a reference branch, etc. So normally, you're not really done with the design really at this point. So you have to say W1, L1. So this is going to be NW1, L1. Why do you want it to be larger? Because you don't want to draw the same amount of current as your main branch, because you will be wasting all of this current, right? So if you're establishing, let's say, 100 microamps here, I want this to be like 2 microamps, 1 microamp, 5 microamps, right? Because otherwise I would be burning twice as much power, and half of it is burned in this like reference branch. How do I choose these sizes? Well, there's a W2 over L2 here. I should have used 1 and 2 here, but it doesn't matter. So again, we can look at the specific numbers, and we will. But it's essentially, if you make this W over L small, your GM is going to be small, because your GM is dependent on square root of that, right? If you make this L too small, your RO is going to be small. If you make your L too large or W too large, the product of those things determines the capacitance of the gate capacitance of this thing, and that's going to determine your speed. Now, exactly what, depending on what you're trying to do and what speeds you're trying to achieve, you pick different places in this trade space. But again, that's where it is, it's trade-offs of the parameters. So again, right now, qualitatively. Okay, so let's say this was not enough. Let's say this was, you wanted to make sure that you have first of all, you have the capability to drive a load. What would you do? Let's say I have a 50 ohm load that I need to drive. Yes. Yeah, you can put, for example, a source follower, right? You can take this here and use a source follower here and drive the load. Now, if I do a source follower, I have limitations of the source follower, right? I have to worry about that. So let's make this another rail. Let's say negative VDD. Let's say it's a bipolar or two-sided supply. Now, okay, so let's say my load is 50 ohms, for the sake of argument. If I do this, and I want to be able to do as close to a full swing as I can. Let's say my supply is plus minus 3 volts. Okay. So what's the maximum current I need to be able to draw if I want to go close to 3 volts? So it's 3 volts divided by 50 ohms, right? Whatever that is. So that's like 6 volts divided by 100. So it's like 60 milliamps, right? So I need to make this 60 milliamps if I were to use this kind of stage. Again, this is not the best stage to use for this, but as a starting point, right? So, okay, so I make this 60 milliamps. How do I make this 60 milliamps? Well, we put a transistor here that nominally for the M times W1 L1 can draw 60 milliamps off of that. So that may be a large scaling here, but that's fine. And then you have to make sure that this guy can draw this kind of current without dropping significant amount of delta VGS, which means that probably it should have a reasonably large W over L. Again, qualitatively, right? So that's where you start off with something like that. So now it's becoming a little bit more sophisticated. So you have a follower here. And you have to make sure that it allows you to drive, so you have to adjust it and make sure that the currents are large enough so that they can drive the RL. Again, not necessarily the best way of doing this. But that would be the essence of it. Now, what if even in this case, what is the gain of this OpAmp? Let's say this is designed so that the gain of this stage is not a limiting factor. We will calculate this going forward. But let's say this is not the limiting factor. The gain is going to be still determined here, right? Now, with this buffer stage that we put here, this follower stage that we put here, what is the gain now? The gain is back to that thing, right? Because now this is infinity from DC perspective. So that's the nice thing about MOSFETs, because the input impedances that they present, at least at DC, classically, it's large. And you will see that this is not the case in bipolars when we make bipolar op-amps. So we have to do a lot more, actually, to get around that problem. But we'll get there. So the gain is this. So what if we want to get the gain larger? What if we want to improve the gain? Do you see any solutions? Can you offer solutions? If, let's say, gain of 50 is not enough, what do we do? You can use Cascode, for example, right? You can make this stage higher gain. So what does that look like? Well, so you make each one of your stages a cascode. So let's say you have something like this. So this is your input stage, but now it needs to be cascode. So let's use a current source temporarily here. And then you want to make a cascode stage. You make a common gate, right? So this is your lower cascode. Of course, if you want to really get the full gain, both of them need to be cascode. Otherwise, the one that's not a cascode will dominate the output resistance. It will present a much lower output resistance. It will dominate. So both of them need to be cascodes. So you need to make a cascode up here. And if you are trying to get your single-ended output from this stage itself, you can do something like that. So you have a cascode current mirror. These upper 4 transistors are a cascode current mirror, right? It's just a better current mirror. If this is a current mirror, these top 2, right? These two just make it a better current mirror because it has a higher output resistance and better matching. These things. Of the force, matching is not the right word. It actually forces the two currents to be better matched or more equal. So, all right. So that's plus VDD. You can go to negative VDD here. And so this would be your input VIP and VIN. This is your output. We'll need to do something with that. So what is the gain of this thing if it was properly biased? Right. So again, the same deal as before. If you're in doubt, this is going to be VID over 2. This is going to be negative VID over 2. And then this is going to be GM, let's say GM1 VID over 2. And this is going to be reflected here, GM1 VID over 2. This current for change of polarity is going to be GM1 VID over 2. So it's going to be forced into this node, GM1 VID over 2. This is going to get reflected down here. It's going to get GM1 VID over 2. The total impedance on this node looking up, what do you see? Let's call this M1, M2. So let's call this 1, 2, 3, and 4. Right? So what is the output resistance looking up? It's the intrinsic gain of this thing times the output resistance of this guy, right? We've gone over this stuff. So this is RO4. This is therefore going to be GM3 RO3, the intrinsic gain of this thing, times RO4. What is it that looking down? Now it's the intrinsic gain of this guy times the output resistance of that, which is going to be GM2 RO2 RO1. I mean, there's a +1 there, which is like, we drop those things unless you're some degenerate cases. Okay, so what is the total gain? It's the GM1 times that, right? So the total gain of this thing is GM1 times the output resistances of these two. You can write it as total R out, but you can also spell it out, which would be this thing, GM3 RO3 RO4 parallel GM2 RO2 RO4, right? Times GM, times GM1. it should make sense. I mean, the specifics don't really matter. You should be able to generate them. There are so many different combinations of these things, right? That you need to kind of like understand how you arrive at them as opposed to the specific answer for the specific kind of solution, because every time it looks different. Now, this kind of at least provides more, it appears to provide more gain, right? Because the GMRO based on the numbers we wrote are in the range of 100, right? So we go from 25 kilo ohm-ish to times 100, this becomes 2.5 mega ohms, parallel 2.5 mega ohms, times 4 millisiemens. It's 425 mil, it's like 10, so it's like 5,000, right? It's a gain of 5,000, roughly. That gives you. So it's fine. You went from 50 to 5,000, which is okay, which is good, which is a good improvement. Now, does this work the way I drew it? First of all, of course, we have to deal with this. We'll deal with that in a second. But would this work? Is it missing something? Other than that current source. Let's say we make this current source right. That's not the problem. Say again? Headroom, yes. If it were working, then I would have to worry about headroom. The way I've drawn it, it doesn't even work. It doesn't do anything. It has a gain. It has no gain. Yes.
There's nothing driving the gates.
Exactly. There's nothing driving these gates. These gates are floating. Right? So there's nothing biasing those gates. I have to come up with a way of biasing these gates. So how do we bias these things? There are thousands and one ways of doing that. But let's talk about some examples. So what I need for these gates, I'm going to draw a lot of current here, right? So I need something that can produce a little pathway for some leakage, some bleed current to go in there, something to just bleed in there and then provide the current. There are many different ways to do this. The one thing you want, though, is that, let me ask you this question. If you want to maximize your headroom, you brought up a good question of headroom, right? You mentioned that. The question is that how should we, what is the ideal voltage this voltage can be? What's the best voltage I could set it at if I had a choice? And I wanted to maximize my headroom, the maximum. So basically from this end, I want this voltage to go, this voltage to be able to go as low as possible before any of these guys crunches, before any of these two becomes basically, goes into triode, right? So when do these go to triode? Let's think about that. How low, what is the lowest this can go? This can go to delta VGS above this point, right? Before it goes into triode. The VDS can be as high go as low as delta VGS before. The delta VGS is the gate overdrive here. So that's fine. So there's a delta VGS here. And ideally, I want this to be no more than another delta VGS, right? That's the best case scenario. So if this is 2 delta VGSs above here, this means that this voltage has to be a VT plus 2 delta VGS above this point. Do you agree? Because you need a VT plus delta VGS here across the gate source here, and you have a delta VGS here. So this voltage, the best case scenario for it is VT plus 2 delta VGS. Well, this is becoming microscopic. VT plus 2 delta VGS. That's what you want it to be at. How can you get VT plus 2 delta VGS? Well, for example, if I have a diode connected transistor here that has a proper current flowing in it, let's just, I can choose its W over L to produce this delta VGS, right? But still, we haven't solved the problem because there's no pathway for current to flow into this thing. These things can only draw current. Do you agree? So we need to provide a pathway for that. So with your permission, I take this out of here and put it on this side so we have room to play with things. So, okay, I still need to provide current to this thing. Right? What's the best way to do that? Well, the easiest way is to put a current source up there. Now you choose this current source to be a small fraction of this current source, right? Because you don't want to be using all of that current to feed this thing, right? So you can make it 1/100th of that, right? So whatever is this I tail, you make this I tail over 100. And then you choose your W over L so that for that current, it would give you the same VT plus delta. It has twice as large as delta VGS. And it's a calculation you can make. So you make that current in such a way. Now, how do we actually do this? Well, of course, this will be a current source. It can be a single or cascode current source. Well, we can make it a single, right? And then this is a tail current source that can be a single. And by choosing this W over property, you can set this voltage to be right so that when it's fed with like 1/100th of that current, it would set this voltage the right way. Okay? So at least we get it biased. Now, is this an OpAmp? Yeah, it's an OpAmp with a gain of 5,000 as long as the load is not resistive. You put a gain of, you put a load of 50 ohm there. What's the gain? Again, 0.2. Right? So you want to definitely make sure that the load, there's some, if you apply resistive load, there's something in between. Otherwise, you've wasted all the effort that you put into making something like that. Now, so we'll continue this discussion. We'll build more sophisticated op-amps, both MOSFET and bipolar, and see why those topological choices are made. The key here, the most important thing, is not these specific examples. I mean, these are good, these are examples. The key is to understand the thought process. Why everything is where it is and what it does. Because when you do that, then you can construct new designs. Yes? No. Sure. Yes, this is actually incorrect. Thank you. This should be RO. No, sorry. This is GM3, that's RO3. This is RO2, this is RO1. Yeah. Thank you. Thanks for that correction. Any other comments or corrections? Yes. Very good. Thank you.